Okay, Assalamualaikum dan salam sejahtera. So, welcome back to our part 3 of lecture series on AC meter. So, we'll continue now on how to calculate the multiplier resistor, RS, this value here, right, using for AC voltmeter using half-wave rectifier. So, there are basically two methods. The method number one is called using DC sensitivity method. Okay, so at first you need to calculate the DC sensitivity method of the AC voltmeter using this formula SDC. Sensitivity DC sensitivity is 1 over the full scale deflection current of the DC. Okay, and then after that the multiplier resistor can be calculated using this formula, which is RS equals to SDC that we calculated earlier in this part, multiply the DC voltage minus RM. So remember that the DC voltage here is basically the average voltage. Yeah. Okay. So yeah, it's given here. So DC voltage is 0.45 multiplied by the the DC voltage equals to for half rectifier is 0.45 multiplied by RMS voltage. Okay. So normally if you have a sinusoidal voltage, AC voltage given to the input, the value is given either the RMS voltage or the peak voltage. Okay. So it depends. So method number two is called what we call a direct method. Okay, so the multiplier resistor can be calculated using directly this formula. So RS equals to VDC divided by the full scale deflection current of DC minus the internal resistor of the uh, voltmeter. Okay, and then method number three. Sorry for my typo. This is method number three. Number three. So you can use an AC sensitivity method, which is the formula is given by SAC. The sensitivity, AC sensitivity is equal to 0.45 multiplied by the SDC. Okay, so then if you calculate SDC from up here, okay, you get this value SDC, you bring it down here, okay, and then you can calculate the multiplier resistor just the using uh, sensitivity AC multiplied by VRMS. Okay, VRMS, and then minus the internal resistor of the meter. Okay, now let's do one example here. So let's say you are given this circuit here. You have, let's say, the input voltage and AC voltage with a 10 volt RMS voltage, and you connect it to a half wave rectifier circuit. Okay, this is a half wave rectifier circuit, and you connect the half rectifier circuit to a DC DC meter, PMFC meter, which has a full scale deflection current of 1 milliamp and internal resistance of 200 ohm. So the question is calculate the multiplier resistor of the RS here, okay, of the meter. Okay, so let's use method number one. Okay, so if you use method number one, okay, you can calculate let's say using sensitivity of the meter using DC sensitivity. Okay, so SDC is 1 over the full scale deflection current is 1 over 1 milliamp, and you have the sensitivity, the DC sensitivity is 1 kilo ohm per volt. Okay, and then you plug in the DC voltage and the DC sensitivity into this equation here to calculate the multiplier resistor, which is equals to SDC multiplied by the range here. The range here is basically the VDC here. Okay, the VDC. The range here is equal to VDC. Okay, so minus the internal resistor of the meter, which is 1 kilo ohm per volt multiplied by 0.45 multiplied by ERMS or VRMS, the same thing. Okay, in this case, I say E is equal to V, doesn't matter. Sometimes the voltage is notated by E, sometimes by V, but it's the same thing. Okay, and these two, you minus that to the internal resistance of the meter. So you plug in the number, and then in the end you will get the multiplier resistor is around 4.3 kilo ohm. Okay. Okay, if you want to use a direct method, you can still use that. let's go ahead, do this example. So Rs is equals to, this is the formula here, okay, is VDC. VDC is again 0.45 multiplied by the RMS voltage divided by the full scale deflection current, and all of them minus the internal resistance of the galvanometer. You plug in the number and you will get the same result, 4.3 kilo ohm. Okay. So let's take a look at another example. Okay, this is another circuit which uses also the same half-wave rectifier. Okay, but with a different deflection current and a different meter resistance and a different number of voltage. So basically, you can, if you want to follow the method, is the same, except you're changing the value of the parameters. Okay, so using, for example, the sensitivity method, the DC sensitivity method, you will get the multiplied resistance equals around 450 ohm, 450 kilo ohm. Sorry. And if you use a direct method, you will get the same monitor. Up to you, you want to use whether method number 1 or method number 2 will get the same results. Okay, this is another example. I think I'm gonna skip this example since I think it's pretty straightforward and just use the same formula, so you can use it as your part of your exercise or study lah. All right. So okay, before we move on, basically half-wave rectifier has some limitation. Okay, some of the limitation is that if you have a different waveform shape, then you have to do some separate calibration lah. And then after that, if you have a different for both positive and negative cycle, there will be a different loading effects. And the rectifier diode voltage drop causes the signal to be non-linear for low level of AC voltage. If you remember that for diode, remember the characteristic wave of the diode. If you remember, it is something like this. Okay, so this is basically a non-linear kind of relationship. If you have a very low voltage, low level voltage around here, okay, so around here very low level, and then the scale to be a bit non-linear. Okay. So DC component also affect readings. Okay, and the rectifier capacitance changes with frequency and thus bypasses portion of the signal. And finally, the rectifier, that the temperature also affect the measurement, because the diode also is affected by temperature. So if you use the ambient temperature, maybe you get different result. If it's high temperature, maybe you get the different results. So how to improve that? So one way to improve the half-wave rectifier is to add another resistor here, another diode here, which is D2. Okay, so commercially, a D2 is inserted in any half-wave rectifier kind of AC meter. Okay, so the additional of D2 reverse bias, as you can see that the current only the D2 is arranged in such a way that the reverse bias on the positive half cycle, and it has virtually no effect on the behavior. It just stay there, and it prevent any leakage current, stuff like that. So if the negative half cycle, in a negative half cycle, meaning that during this is a positive high cycle, this is a negative high cycle. Okay, so D2 is forward biased and provide an alternate path for the reverse bias leakage current that would normally flow through the meter movement of D1. So it will provide some, basically during negative cycle, right? Positive cycle current goes this way, but negative cycle current goes this way, right? So it will provide an alternative path for the leakage current to flow, okay, not through the diode D1. So basically, and then there's another resistor here, R2. Instead of D2, they also the improved half rectifier circuit also include R2. Okay, so the purpose of our shunt resistor R2 is to increase the current flow through D1. Okay, during positive half cycle, so that the diode is operating in a more linear portion of its characteristic curve. As I mentioned before, one of the limitations is that the diode will perform poorly for a very low voltage, but if you put R2 here, there will be more voltage pushed, a current pushed to the rectified D1, and you will move away from the nonlinear portion. Okay, so although this resistor improve the linearity, is also further reduce the AC sensitivity. Okay, let me show you the formula how to solve these parameters of for the improved half-wave rectifier. Okay, so to calculate resistance, okay, you know that the VM, the meter voltage, is the full scale deflection current multiplied by Rm, and we know that the shunt current is VM divided by the shunt resistance, and the total current, this current here, is equal to the shunt current plus the meter current. That's all. That's all. It's all just Ohm's law and KCL, right? And then I want to remember that for the half rectifier, the DC voltage is 0.45 multiplied by the RMS voltage. So if we combined all these 1, 2, and 3 formula, okay, so you can find that the total resistance is VDC divided by IT, and it's also equals to R1 plus RD plus the parallel resistance between meter Rm and R2. Okay, so that's how they calculate the total resistance, and you can calculate the limited resistance. Okay, I forgot to mention that the R1 here is what we call the limited resistance instead of multiplier resistance. Okay, is if you rearrange back this equation here, you will calculate R1 is equal RT minus RD minus all these two parallel resistors. Okay, so to calculate the AC sensitivity is just AC divided RT divided by VRMS. Okay, and to calculate the equivalent DC sensitivity is STC is 1 over I total, or STC equals SAC divided by 0.45. Okay, so let's take a look at one example before we end this part 3 of the video. So you have this circuit here. Okay, this is I total, sorry to mention, this is I total, not IF. Okay, you have a meter here in parallel for shunt resistor of 200 ohm, and the question asks you to calculate the series RS series multiplier resistor and the AC and DC sensitivity. Okay, so the value of the multiplier resistor is RS, so you calculate the shunt current first, is EM over RSH, and EM is actually I deflection current multiplied by the RM. Okay, so remember from the previous formula, it's equal 100 microamp, and the total current is I shunt current, which is this current here, plus IM. IM is the meter current. Okay, and you have 200 microamp, and VDC is 0.45 multiplied by ERMS. So you have 4.5 volt of the DC voltage. So and then the total resistance is EDC divided by IT. EDC is come from this equation here. And I total you calculated from here, 200 microamp, and you plug these two value and you have 2 to 2.5 kilo ohm. Okay, so the total resistance, remember from the first formula, you can calculate that RT is this formula, and if you rearrange that, you will calculate for the shunt resistor. Okay, you plug in the RT, RD. Okay, the R diode basically is, let's say it's assumed is 50 ohm, because the diode here also has some sort of internal diode resistance. Okay, this is RD. I forgot to mention that. Okay, but it's okay. So let's say RD here is, RD basically is RD1 plus RD2. Okay, it's the average. Okay, the diode for 1 and the diode for 2. Okay, so it's given, it's not, you have to calculate that and multiply by this these two parallel resistor lah. Okay, and then after that, then you can calculate your RS, which is around 22 kilo ohm. So and then the SAC is RT divided by range, as RT you calculate before, 22.5 divided by range, 2250 ohm. Okay, volt, ohm per volt. So and then the SDC is 1 over IT, is 1 over 200. This is microamp, sorry about that. And you have the AC, and you calculate the DC. The DC is SAC divided by 0.45 is around 500,000 volt per volt. Okay, thank you very much. I'll see you again in the next video for our next topic. Okay, see you again. Thanks. Bye bye.